So before we go on and talk more about vector operators next week, for the last bit of this lecture, I'd like to talk a bit more about dimensional analysis. Now, dimensions have been very important throughout our physics careers. We can immediately tell when an equation is dimensionally wrong, that it must be wrong. That means that we can usually find the correct factors and powers of things that have dimensions in our equations. In order to get something with dimensions wrong, you have to get it really quite spectacularly wrong in several factors before you sort of have something that is dimensionally correct again. So it's a very useful corrective tool, and we also use it predictively and suggestively when we're noting that various quantities, our operators that we were looking for, were in fact, of momentum or angular momentum. We guess that that might be the property we're after. But dimensional analysis is very useful when analyzing systems as well. And the reason we're talking about this now is that it's going to be a useful tool when dealing with your project. But I'd like to bring it up in terms of, say, a quantum mechanics example to illustrate the usefulness. So let's take a very simple example like a quantum system. We know Schrodinger's equation. So there it is in general. If we have, say, a system with one spatial degree of freedom, we could put this into the position basis and get an even more familiar version with a kinetic energy term and a potential term, and maybe that's a harmonic oscillator. There we go. And so this is the kind of Schrodinger equation that you're used to. This is just the equation of motion for the coefficients when we put that into the position basis. The thing is, this depends on various parameters. It depends on h bar, it depends on m, it depends on omega. And so there are three parameters. Maybe you have to keep changing all those parameters and solve this again and again and again to get the same answer. But in fact, dimensional parameters can get you in trouble. So what I'm going to do is I'm going to deliberately put this into dimensionless units. And so I'm going to pick some time scale. So tau is going to be dimensionless, not dimensionful. So it's going to be proportional to t, but we're going to divide it by some time scale. And r is going to be dimensionless, and it's going to be proportional to x, but again divided by some length scale, x naught. And now I'm going to put this equation here into that. So IH bar, we know from the chain rule that this derivative with respect to time can be turned into a derivative with respect to tau. I can tell I got that right because this had time dimensions on the bottom and this has time dimensions on the bottom, so that's fine. And so forth with this. We can go to dr squared, and I know I need a 1 on x naught squared to get my units right, and indeed if I check my chain rule that's what it will be. Now we can group these things. If I multiply both sides by t naught and divide by h bar, I can push this part down to something that's purely dimensionless, and so now every other term is going to have to be purely dimensionless. So these objects here, this big cluster of things and this big cluster of things, must be dimensionless. So I can make them equal to anything I like. For example, I could make them equal to 1. If I was trying to make this equal to 1, then I'd have to set, then that would be 1. If I plug that into here and I want to set all of this to 1, then I would have, so by judicious choice of x naught and t naught, and this t naught, if we plug it in, by the way, we're going to get 2 on omega, which is fairly obviously a time scale, a natural time scale of the system. So by judicious choice of t naught and x naught, we've managed to make this equation very simple indeed. What's important about that? Well, first of all, we don't have an h bar, an m, and an omega. It was kind of obvious from the start that the only thing that mattered for this term wasn't h bar by itself, but h bar squared on m. And so there was no need to change those independently. Well, it turns out there's no need to change anything at all, because all you ever change by changing omega, h bar, and m are what you really mean by the time scale and the length scale. So I can solve this equation here. So this equation here, which has no free parameters, I can just plug in an initial condition and fire it off, and I know what this equation does. If I analyze this equation, I am done. The only thing I would ever do if I changed my physical parameters here is I would relabel my axes. Now what if we were to add an extra term? Supposing we were to add plus k to the fourth x to the fourth in our potential there. Then of course this would give us a new parameter, and down in here we would end up with an extra term. And this here would be a dimensionless parameter. And that parameter would matter. So suddenly we would have a one parameter system. So by adding all these terms, we've got h bar, m, omega, and k here. And what we'd actually have to solve is we'd have to solve a family just with one parameter, where we'd be changing one parameter across the family. And so now if I knew all the different behaviors of this equation for different values of alpha, I would in fact know all the possible ways that this equation can be solved. And this kind of dimensional analysis, the idea is you can reduce what look like very complicated systems down to their minimal set so that you don't keep on recalculating things that you ostensibly have in fact already worked out.